Okay, welcome to this. This is the fifth lecture that I am delivering today. Okay, so I think I should write this in bold letters. It is fifth lecture. Okay, it is the fifth lecture, and we are studying on the topic solutions. Okay. Now, why am I giving stress on this fifth lecture? Is because any student who wants to go through this fifth lecture, okay, please make sure that you have already gone through the first, second, third and fourth lecture, okay, so that you will be able to get the continuity and so that you will be able to follow this complete lesson. Okay, so this is the fifth lecture that I will be delivering today. What we are studying in this, during all these lectures are matters related to solutions. Okay, solutions. Okay, which is the second unit of higher secondary chemistry. All right. Okay. All right. So now, in the last lecture, that's the fourth lecture, what we studied was Raoult's law. This is what we studied. Okay. Now, whenever you want to study any law or any theory in whether it is science or any other subject, okay, we explain the law or we explain the content using the statement of the law, okay, which we have done already in the last class. Then we elaborate the law using the mathematical statement. Which also we have already done in the last class. Okay. Now, after doing the statement of the law and the mathematical statement of the law, we conclude by graphical representation of the law. Okay, so this is what we are going to do today. That is the graphical description of the Raoult's law. Okay, so Raoult's law, graphical depiction or representation. Graphical depiction or graphical representation. Okay. Now, okay. So again, let's make some assumptions. Okay. So if A and B be two liquids, all right, and if PA, PB be the two liquids in a mixture, of course, in a mixture, and PA and PB be the partial vapor pressure of A and B, of course, of A and B respectively, and PA naught and PB naught be the vapor pressure of pure liquid, pure A and pure B respectively. Okay, all right, and one more assumption, XA and XB be the mole fraction of A and B in the mixture, of course, in the mixture. Okay, so according to Raoult's law, You have already done this in the last lesson. PA is equal to PA naught into XA, and this is with regards to the component A. With regards to the component B, we can write down PB is equal to PB naught into XB. Okay, last lecture this was done. All right. Okay, now we have a space this thing. Okay, all right. Okay, now let's first of all, let's to represent PA equal to PA naught into XA. Supposing I want to represent only this, PA is equal to PA naught XA, then what I can do is I can make, okay, let's make a graph here. I can make two axes. All right. PA, you plot, this is your y axis and this will be your x axis. All right. Now let's plot PA on the, okay, I'll just let me partition so that there is no confusion. Okay, so the PA or the partial pressure of A I am plotting on the y axis, and XA I am plotting on the x axis. All right. So you can see PA is equal to P naught A, PA naught into XA. Okay, and you have already studied that. Now this will be from 0 to 1. All of you know that mole fraction, I think I told you last time that mole fraction, the sum of mole fraction, okay, because you know that XA plus XA plus XB is always equal to 1, which means the total mole fraction possible for a component is 1. Okay, and if the mole fraction of one component is 1, that means what? That means that component is pure. All right. Okay, anyway, we will come to that again later on. Okay, now see, PA is equal to PA naught into XA. Now when we are plotting, PA naught is a constant. All right, when we plotting PA versus XA, we are plotting this is a graph of PA versus XA. All right, how do you do that? That means supposing when XA is equal to 0, then PA will also be equal to 0. All right, why? When XA is 0, then PA is equal to something into 0, it is equal to 0. All right, otherwise even if you do this experimentally, okay, so what do you do it, how do you do it experimentally? I'll just show you. Graphical representation means experimentally you have two sets of, you get two sets of values. What are those values? You find how much is PA. Okay, how much is PA? Otherwise, you take the mole fraction. You take the mole fraction of A. Supposing the mole fraction of A is say 0.1. Then find out how much of PA will be. Okay, you find this out. Then you change the mole fraction of A. Supposing the mole fraction of A is 0.2. Find out how much of PA. Change the mole fraction of A is 0.3. Find out how much of this thing. This way, you take the mole fraction of A, say 0.9. Find out how much of PA. Okay, now that is how you plot. That's how you plot in a graph, right? That is how you plot in a graph. That means now you are plotting coordinates or pairs of PA and XA. When XA is equal to when XA is equal to 0.1, what is PA? When XA is equal to 0.1, PA is equal to supposing a certain number here. When XA is equal to 0.2, PA will be equal to something here. When X is equal to 0.3, something here. So this way, when XA is equal to, otherwise, okay, let me redo this. Okay, supposing these are the different values of PA when X is equal to 0.1, 0.2, 0.3, 0.4. Okay, this way, if you join these points, you get a straight line. All right, you get a straight line. So experimentally, see this is experimentally, this is the type of graph you get when you plot PA versus XA. Okay, taking y-axis as partial pressure and x-axis as the mole fraction. Okay, now when you extrapolate this graph, to the value when XA is equal to 1, XA is equal to 1. This XA is equal to 1 value, see. Okay, so this indicates XA is equal to 1. So when XA is equal to 1, okay, this value of P naught PA, this value will be equal to P naught E. All right, because see, when XA is equal to 1, PA will be equal to what? 1 into PA naught. Okay, from this equation also you can find out PA is equal to XA is equal to PA naught. Okay, so therefore when XA is equal to 1, that value of PA will be equal to PA naught. Otherwise, what is PA naught? PA naught is the pressure exerted when A is pure. A is pure means when B was not there in the mixture. All right. So this is the type of graph you get. Okay, when you are plotting out of these two, out of A and B, you are plotting only A. You are plotting only A. Okay, A component. That means you are plotting the partial pressure of A versus the mole fraction of A. This is the type of graph you get. Okay, now, but what is more important is the graph you get when you are plotting both PA and PB. All right. Okay, so graph. Now this is what we can call graphical representation of Raoult's law. So in the graphical representation, what we do is we draw y-axis, which will contain naturally the pressure terms or the partial pressure, vapor pressure, and on the x-axis we take the mole fraction. Okay. Now in this particular graph, okay, this we are plotting what? We are plotting, or it's the plot of partial vapor pressure of A and B against, okay, mole fraction of A and B. All right, it is so therefore, since it is a plot of partial vapor pressure of A and B against the mole fraction of A and B, the graph you get here will be two lines. Okay, one for A and the other for B. All right, now, okay, now the interesting thing here is that there will be two y-axis. Here there will be two y-axis. Why there will be two y-axis is because the x-axis is limited, has limited value from 0 to 1. Okay, there is a important thing that we have to remember. The x-axis has limited value, or the x value is limited between 0 and 1. So since it is limited, we have two y-axis. Okay, so the x-axis ends at 1. This is the x-axis, but it ends at 1. Okay, so this is the partial pressure. All right, you are measuring in atmospheres or bar, and this is the mole fraction. Okay, and mole fraction is measured from 0 to 1. Okay, supposing this is the mole fraction of the B component only. Assume. So if this is a mole fraction of B, all right, if the mole fraction of B, then the mole fraction of A will be measured. It will be measured from in the reverse. That means, okay, it is like this. See, if XB is 1, see, this is XB. So XB is 0 here, XB is 1 here. If XB is 1, it means XA will be equal to, if XB is 1 here, all right, let me make this a partition. Okay, so if XB is 1 here, Okay, it means XA will be equal to 0. All right, this is what you should try to answer. Why it is it should be equal to 0? Because XA plus XB is equal to 1. Okay, since XA plus XB is equal to 1, okay, so since XB is 1 at this point, so XA will be equal to 0 at that point. Okay, similarly here, okay, in the origin of the graph, XA or XB is equal to 0 here, and if XB is 0 here, it means XA will be equal to 1. Okay, so this is how you should first of all understand the graph. How? That means the y-axis is measuring the partial pressure. There are two y-axes, and the x-axis measures the mole fraction, and the mole fraction, the range of mole fraction is from 0 to 1. Okay, in the origin, okay, XB is 0, and in the origin XB is 0, therefore XA is 1. Okay, and here XB is 1, which means XA will be equal to 0. Okay, so now first of all, let's draw the graph for let's draw the graph for this. Graph for PB is equal to P naught B or PB naught into XB. Okay, so you know the graph will be something like this. It will start from 0 and it will hit the y-axis at a certain point. Okay, so this let's say this is the graph of PB is equal to PB naught into XB. Okay, so you can see as XB increases, PB also increases. See, XB is equal to 0.1, XB is equal to 0.1, PB is here. This XB is equal to 0.2, PB is increasing. XB is equal to 0.5, PB is increasing. 0.5 here, PB is increasing. Okay, so as the XB value increases, PB value also increases. Okay, so that is the first graph of PB is equal to P naught B into XB. Okay, so in this graph, other things you should know is that what is this point here? This point here, this represents what? This represents PB when XB is equal to 1. So when XB is equal to 1, then PB will be equal to P naught B. So therefore this point here represents P naught B, or it represents the partial pressure of B when it is pure. It represents the pure the partial pressure of pure B. That means when and in the absence of A. All right. Okay. So now in the this is the graph for PB versus XB. PB versus XB. Okay. Now next, let's draw the graph of PA versus XA. So the graph of PA versus XA will be something like this. It will be something like this. This will be the graph of PA is equal to PA naught into XA. Okay. Don't confuse with this graph. Why? In this case, in this graph I showed you just to show how the plotting is done in a graph, okay, of PA versus XA. In this case, the mole fraction axis, you can see the mole fraction axis was started from 0 to 1. Okay, that is 0 to 1 is the mole fraction of A. But in this case, the mole fraction of A starts from here. It is XA 0 from 0 at the end equal to, and x is equal to 1 in the main origin. Okay, so for x-axis, for the A component, mole fraction start. This is the origin for A component. It means x is equal to 0 to x equal to 1. So that's why we are having a graph with a negative slope. So this is the graph for PA is equal to PA naught into XA. All right. So similarly, you can say that this point in the graph represents P naught A. All right. Why? Because when XA is equal to A, XA is equal to 1. When XA is equal to 1, it means P naught A, or it means PA, or the partial pressure is equal to partial pressure or the pressure of pure A. Understood? Okay. So these are two graphs of both PA and PB. Graphs are both A component and B component. Okay. Now all of you know that the total pressure, you know that the total pressure, okay, all of you know that the total pressure P is equal to PA plus PB. Okay. So where is this P, or where in this graph, where do we find P is equal to PA plus PB? You find this by joining these two corners. Okay, this should be a straight line, sorry. Okay, so this represents P equal to PA plus PB. Okay, so this is the graph. This is the graph. This particular is the graphical representation of the Raoult's law. Okay, but assuming that you have got two components A and B, you have got two components A and B, all right, in a mixture, all right, and then on top of that mixture we have got vapors, all right, vapors are both A and vapors are both B. Okay, now we are assuming that PA and PB are the partial vapor pressure. We are assuming that PA and PA naught and P naught B are the pure vapor pressure. We are assuming that XA and XB are the mole fraction of A, where they are the mole fraction of A and B in the liquid mixture, not in the vapor, mind you. Okay, so therefore, according to Raoult's law, this is something we have already done. We have already done in the 4th lecture, and this is if you want to show the graph of only one component, that is component supposing A. Okay, now this is if you want to show the graph of both the component A and B. Okay, this is the graphical representation of the Raoult's law. Okay, so you will see this carefully, and then I'll rub it off. All right, now before we do the next topic, this is graph of Raoult's law. Briefly, I will just explain to you. In the graph of Raoult's law, this is the mathematical form of Raoult's law with respect to one component. All right, and graph will be if this is PA and this is your XA, then the graph looks something like this, straight line. Okay, let's draw. Okay, straight line passing through the origin, straight line passing through the origin. Okay, now what I'm trying to take you from here is, those who have studied mathematics, okay, those who have studied mathematics, you must be aware of the relation y is equal to mx. Okay, this is y is equal to mx plus c. Okay, y is equal to mx plus c. This is the equation of a straight line. Equation of a straight line, and y is equal to mx is the equation of a straight line passing through the origin. Okay, y is equal to mx. This is the equation of a straight line passing through the origin. Y is equal to mx plus c is the equation of a straight line not passing through the origin but having a intercept as c. See, this is what it means. See, supposing let's make it here. Supposing this is your graph. It's a graph paper, and we have y axis and the y axis. In the y axis, we plot the y terms. In the x axis, we plot the x terms. All right. Okay. Now, supposing we get a graph like this, something like this. If you get a graph something like this, it means this is C or the y coordinate, okay, or the y intercept. The C is the y intercept, or the y intercept means the point on the y axis where the line is cutting. All right, okay, and m is supposed to be the slope, but that is not relevant to us, okay. But when C is 0, it means the line is cutting the y axis at 0. Okay, so if this is the equation of y is equal to mx plus c, then the equation y is equal to mx will be something like this, passing through the origin. The equation y equal to mx, this will be the equation y equal to mx. See here, c is 0, because this is because the line is passing through origin 0. All right. So now, why I am telling you all these things regarding about mathematics is because, okay, the equation of Raoult's law, that is P equal to P naught into x. Okay, I am just ignoring the component A terms. Okay, the equation of the Raoult's law is partial vapor pressure is equal to pure vapor pressure into mole fraction. You compare this with y is equal to mx. See, if you compare this with y is equal to mx, your p and y, they are the quantity is plotted on the y axis, and x the mole fraction, this is the mole fraction of capital X, mole fraction x, and this small x terms, they are the quantities plotted on the x. Okay, so comparing these two, okay, even without doing it experimentally, even without finding PA and XA experimentally, we can conclude just by comparing the Raoult's law expression with the y is equal to mx, we can conclude that this will be a straight line passing through the origin. All right. Okay, this is the straight line passing through the origin. Okay, now that is what we are doing is we are using the knowledge of what do you do here? This is y is equal to mx plus c. Okay, something wrong here. Okay, now what we are doing is we are trying to use the knowledge of mathematics, coordinate geometry, the knowledge of coordinate geometry in predicting the graph of Raoult's law. If this is the statement of Raoult's law, P is equal to P naught into x. If this is the statement of Raoult's law, it means the plot of P versus x must be a straight line. Okay, because this is comparable to y is equal to mx. All right, now, okay, now, so that is using coordinate geometry. Now, supposing vice versa, let's assume now let's discuss something which is just the vice versa to what we have discussed. Supposing we find for a particular mixture of A and B, we find different values of XA, we find different values of PA, and we plot in a graph. After plotting in a graph, we find that that graph is a straight line passing through the origin. What does it mean? It means supposing we don't know this equation, we have only PA values and we have what XA values, many PA values, many XA values, and we plot in a graph. If the graph is a straight line like this, what we can conclude is that PA is equal to P naught A into XA. Why? Because equation of a straight line passing through the origin will be PA is equal to P naught A into XA. Otherwise, equation of a straight line passing through the origin will be y is equal to mx. Alright, so therefore, experimentally if we plot a graph and find out the nature of the graph, and we find that the nature of the graph is a straight line, it means this particular graph obeys the relation, mathematical relation PA is equal to PA naught into XA. Alright, okay. Now, supposing the graph is not a straight line, Suppose the graph is not a straight line, but the graph is something like this. It is a curve. What does it mean? It means this particular graph or the data that we have got, it is not supporting the mathematical equation PA is equal to PA naught into XA. Alright, that means this particular data that we have got it experimentally is not supporting the Raoult's law, because this relation is the relation of Raoult's law. Okay, so that is something that I am trying to take you. That means whether a given experiment or whether a given liquid mixture, alright, is obeying the Raoult's law or not. How do you know? We can find out whether a given liquid mixture is obeying the Raoult's law by doing an experiment. What experiment? For a particular component A, we find different values of PA at different values of XA. Okay, so we can change the mole fraction from 0.1, find PA, change the mole fraction to 0.2, find PA, change the mole fraction to 0.3, find PA, and if you get many sets of values and you plot the values in a graph, if the graph is not a straight line, it's something like this, then we know that this particular graph does not fit into this particular mathematical relation. If it does not fit into this mathematical relation, it means it is not obeying Raoult's law. But if it is a straight line, like this, passing through the origin of course, then it obeys this relation, and we can say that it is obeying the Raoult's law also. Okay. So next what we are going to do now is, there are two types of liquid mixtures, those that obey the Raoult's law and those that do not obey the Raoult's law. Okay, and they are known as ideal solution and non-ideal solution. Okay. So I'll clear this matter, and so we are doing now. We will do the ideal solutions and ideal solution. First of all, let's do the ideal solution. Okay. Now you can use some background to this. Okay, you have studied in class 11 the gas laws. Okay, Boyle's law, Sal's law, the universe of gas equation. You have studied this in class 11. Okay, and there also you have studied about ideal gas and non-ideal gases, or ideal gas and real gases. Okay, what are ideal gases? Gases which obey the gas laws, they are known as ideal gases. Okay. And which don't obey the gas laws, they are known as the non-ideal gas or the real gases. Okay. Here similarly in solutions, okay, the governing law is the Raoult's law. Okay, Raoult's law is that you can say the governing law on solution. Okay, so those solutions which obey Raoult's law under all concentrations are known as ideal solutions. All right, so let's write down. Okay, solutions which obey Raoult's law under all concentration ranges. Are known as ideal gas, ideal solution. Okay, and non-ideal solution. Non-ideal solution means solutions which do not obey Raoult's law under all concentration, but do so under very, very dilute conditions. Dilute condition. Okay. So those solutions which obey Raoult's law, okay, and under any concentration ranges, they are known as ideal solution. But solutions which do not obey Raoult's law, but solutions which obey Raoult's law, which don't obey Raoult's law at all, okay, but they may do so under very, very, very dilute condition. Okay. So so this is something we have to know about the ideal solution. Okay. Then another important fact about ideal solution is that practically no solution is ideal. Okay. Practically no solution is ideal. Okay. But we have nearly ideal solution. Nearly, so we may have solution practically, strictly, exactly ideal. We don't have such solution. Okay, like if you have studied in class, if you have studied gas laws, you have studied that truly ideal gas we don't have. Okay, but we can make the gases ideal under very low pressure and under very high temperature. Okay, but truly ideal we don't have. In the same way, truly ideal solutions we don't have, but we can make them nearly ideal. But we have some solutions which are nearly ideal. Okay, example of such solution is, say, example, benzene plus toluene. Another example is chlorobenzene plus bromobenzene. Okay, you can say similar type of compounds, similar type of chlorobenzene, bromobenzene, benzene, toluene, similar type of compounds. These are what? Nearly ideal solutions. Okay, or one example, example 2. There are other examples also, or you might have example 3, or very, very dilute solution. Okay, so very, very dilute solutions. Okay, so you have a solution which is you have a solution which is not ideal. Okay, but if you make it very, very, very dilute, then you might have an ideal mixture. Okay, you might have a solution which can behave like ideal solution. Okay, so this is a nearly ideal solution. Okay, then lastly, there are lots and lots of examples about non-ideal solution. In non-ideal solution, liquid mixture, you can take an example of ethanol plus water. You can have an example of acetic acid and water. You can have an example of, say, acetone plus ethanol. Okay, these are all non-ideal solutions. Okay, ethanol plus water, acetic acid plus water, non-ideal solutions. Okay, so I will rub this off. Okay, now, so now graphical representation of deviation from Raoult's law. Okay. All right. So supposing we have got a non-ideal liquid. Okay. Example. Supposing we have got ethanol plus water. Ethanol plus water. Now, if you want to show this in a graph, this will be the graph that you get. Okay. As before, you have the pressure on the y-axis. You can see the vapor pressure, the liquid vapor pressure, and you have got the mole fraction on the x-axis. Okay. Now, this see, supposing you can take there are two components, A and B. Instead of A and B, you have got ethanol and water. Okay. So this will be the plot for say, this is the plot for say water. Okay. Okay, so this is the graph for ideal behavior. All right, and this is the graph for say ethyl alcohol if it behaved ideally. Okay, this is also the graph for, okay, it can be ethanol or water. Okay, but this is the graph that you would have got if this mixture was ideal, or if this mixture behaved, or if this mixture obeyed Raoult's law. If the mixture obeyed Raoult's law, then this is the nature of the graph which will get a straight line. Okay, this is the nature of the graph which will get. Okay, supposing you can call it, this is ethyl alcohol, ethanol versus okay. Right now, but we already said that ethanol plus water is not ideal mixture. It is not ideal mixture, and it will not obey Raoult's law. So, if it does not obey Raoult's law, what will be the graph you get? The graph you get will not be a straight line. It will be bulging outwards like this in the case of ethanol. In the same way, the graph for the next component will be bulging outwards like this. Okay, and the total pressure graph, straight line, if it behaved ideally, this would be the total pressure graph. Okay, but in our case, since it does not behave ideally, the total pressure graph will also be bulging outwards like this. Okay, so this will be the graph of actual graph for, say, this is the graph for ethanol, and this, the other one, this is the graph for water component. Okay, so you can say that, observationally, okay, that is the vapor pressure of ethanol or water is more than the expected. That means, that is, if it behaved ideally, the vapor pressure is more. See, this is the vapor pressure graph, but it is more. So therefore, since it is more than the expected, okay, we say that the deviation is positive. We say that the deviation is positive. Okay, so therefore, those liquid mixture which does not obey Raoult's law, okay, That means it does not obey means they deviate from the Raoult's law. So since it deviates from the Raoult's law, it means in the case of ethanol and water mixture, the deviation is positive. Okay, so this way there are two types of deviation, one positive deviation and the other is negative deviation. Okay, so I will rub this off first of all, and then you can. So this is what we have done so far, and then since there is there is a time constraint, so we will continue with the next lesson. We'll continue with the remaining topic in the next lesson. Okay, so let's revise whatever has been taught so far, and then if you have the book, all right, the book on chemistry, you can go through the book also on whatever lessons that has been done so far, or whatever lessons that will be done in the coming days also. Okay, so see you in the next class once again. Okay, thank you.